This lesson deals with supplemental problem 217. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems starting on page 37. We'll take a look at making a dual complementary power supply. What that means is we're going to create a plus voltage and a minus voltage with the same magnitude. And we use these for powering op amps or power amplifiers. We can do that with a bridge rectifier, a center tap transformer, two capacitors, and basically two loads. You can see here I'm showing V sub C from here to ground, and then showing minus V sub C from here to ground. In other words, we're going to show that this is a positive voltage as shown here, so it's going to be negative with respect to ground. I'd like you to sketch V out 1 and V out 2 and determine the design formulas like we did in supplemental problem 215. Oops, this should be supplemental problem 216. Let's first start by removing these two capacitors, and let's see which direction the current wants to flow. Let's assume that V sub S over 2 is positive and beginning to grow in value, and eventually current's going to flow in this direction. From here through D2, back through here, back to where it started from. Solve for the output. The rise in voltage then would equal minus the drop of VD2 on, plus V sub S, and come back where we started from. And that's this equation right here. And this quantity is positive when V sub S over 2 is greater than 1 diode drop. I'm going to label this as just VD on, assume that all of the forward bias drops are basically the same. But I'll leave the subscripts here as I go through the path for the current. If the input gets big enough, it eventually will have current flowing in this direction. And when this is going positive, it's building positive voltage at V out 1. What's happening for V out 2? Well, when this is positive, current's going to come out of here, go through here, come back through here, and then go back to where it started from through D4. Again, the current's going to come up through here, go through here, come back through here, come back through D4, back to where it started from. Rise in voltage here is going to equal the drop of V sub S over 2 minus VD on 4, and then come back to where it started. Here too, current's going to flow when this is bigger than this. When V sub S over 2 is greater than 1 diode drop, current will begin to flow. That's what this expression here is. But note, this is a positive voltage, but with respect to this node here, it's a negative voltage. The first half cycle, V out 1 is contributed by this one, and this is V out 2 contributed by this one. Because we're putting the ground here, we're making this a negative voltage. What happens when this goes negative and likewise this goes negative? We're going to have a voltage now in this direction, and current's going to come out of here, go down this way, come back through here, back through D1, back to where it started. And the path is going to be coming through here, through R sub L2, back through D1, back to where it started from. You can write an equation. The rise in voltage V out 2 is equal to minus V sub S over 2 minus 1 diode drop for VD1, back to where we started. When this goes negative, it contributes to this output signal. Current will flow when the magnitude of this is greater than 1 diode drop. What about this one? I reverse the sign on this, so this is going to be minus and plus. Current's going to come out of here, go through D3, come back through RL1, come back through here, and come back to where it started from. One more time, we got current coming out of here, going through D3, going through RL1, coming back to where it started from. V out 1 is equal to minus VD on 3, minus V sub S over 2, and then back where we started from. This needs to be in magnitude greater than 1 diode drop for current to flow. Second half cycle of this contributes to this, and the second half cycle of this contributes to this, making both of these voltages positive with respect to this polarity, but again, we're going to ground it here. We'll make this the negative of whatever's here. Let's scroll down and look at those equations. If you add up these two and these two, we're going to get V sub S over 2 twice, and then we're going to get our diode drops twice. Again, we'll drop the subscript on it, and really just cross multiplying by this and getting a 2 over here. The sum of the two power supplies is going to be the value of V sub S minus 2 diode drops. It's really like the full-wave rectifier, but now we're splitting the voltage in half, basically, by putting a ground on the center tap. The same is true over here. If we add these two up, I'm going to get this added to this. I'll get that twice, and I'll get 2 diode drops. Remember, this is going to be negative. This will become a positive number, minus 2 VD on. Let me just summarize what we did on the previous page. We had 2 V sub S over 2 sources, which were sine waves, and they go between some maximum and some minimum, and we'll assume that it's symmetric, a value of V sub M. Then our two outputs were the same, and it was the full rectification of the input minus 1 diode drop for our case without the capacitor. And then different combinations of diodes contributed to each of these humps that are positive. If we put the capacitors back on, what's going to happen? Well, again, we got our same input, but now we're going to charge up a capacitor, And then our input's going to drop, and we'll be able to hold that voltage depending on the value of R sub L and C sub L. We'll come back and catch it with the next part of the cycle and charge it back up and back down again. So this is exactly the same as supplemental problem 216, where we had a maximum voltage minus 1 diode drop. Let's further look into the similarity between this power supply and the one in supplemental problem 216 by going to page 36. What we had with this center tap transformer full wave rectifier is that we've got our diodes between the upper and lower side of the secondary and 2 diodes feeding an R and a C in parallel. If you look at page 37, we have the same thing with this part of the circuit. Here's the upper and lower part of the secondary feeding 2 diodes into an R sub L, C sub L. If you flip these 2 diodes, you have this right here. And this too is feeding the upper and lower part of the secondary. And then the common node here goes to the capacitor and the resistor. Now because we flipped the diodes, we flipped the polarity of the output. Formulas we derived for supplemental problem 216 will apply to this problem for this section and for this section. Go back to page 38. Since we have the same picture as we had for our output voltage in supplemental problem 216, we'll have the same design formulas, except that we have a load 1 and a load 2. We'll take the same formulas we had in that supplemental problem and just put the subscript of the loads 1 and 2. And likewise for the output voltage with 1 and 2. We have an output current for Vout1 and R sub L1, and that was controlled by diodes 2 and 3 and by 1 and 4. That's going to be half of the average current in the load. We have a center tap transformer, so that's the same. Our breakover voltages will be twice V maximum, and let's just go look at the previous page and show that. Take these capacitors off now. Put some numbers in here so it'll be a little bit easier. I'll just do one of these. Suppose that the output voltage here is 10 volts minus, say, 0.7. Let's look at the case where this is equal to 10 volts in this direction. In other words, when it's gone negative. When this was positive, D2 was on, and when it's negative, D2 is off. So let's solve for the voltage across D2 when it's off. What's going to be this node voltage, which is minus 10, minus this node voltage, which is 10 minus 0.7. This voltage will equal minus 20 plus 0.7, 19.3. That's approximately twice our peak value. Go back to page 38 again. And so that's the same formula we had for supplemental problem 216 also. The same is true for the surge current if we break the resistance down into each of the 2 legs in the center tap transformer. And this is supplemental problem 217.